This is chapter 30, problem number 16. In this problem, we're given a rectangular toroid, and it is broken up into several terms. We're given the number of terms h. We're given the height of this rectangular portion here. We're also given the inner radius, r1, the outer radius, r2, and the mid radius, r. So what we have to do is find the self-inductance. We know that the self-inductance, L, is equal to flux over current. So how we're going to do this is we're first going to have to find what the magnetic field is. So we can use Ampere's law. We know that the magnetic field, B ds, integral of B ds is equal to mu naught n I. Even though we're not given I in this problem, you will see that I does not matter because eventually we'll divide it out. So since this is the summation of all the tiny little ds's, it'll essentially become the circumference. And this is a complete circle. This is just a cross-section. So that would become. And if we move that over, we get mu naught b is equal to mu naught I over 2 pi r, the circumference. Now that we have B, we can find what the flux is. So the flux is equal to the integral of dA times B, and then multiplied by n, the number of turns. So we know what dA is because, let's say we break this up into dr. dA is simply h times dr. h times dr. B, we already found that. mu naught n I over 2 pi r. And we're doing this area from here all the way to here. So we're going to be going from r1 to r2. When you integrate this, you get n times h mu naught n I over 2 pi times ln r. This is integrated from r1 to r2. So we will see that it would be this constant over here multiplied by ln of r2 minus this constant times ln of r1. So according to the properties of logarithms, we can express that as a division. So we get mu naught n squared h times I over 2 pi that we multiply by ln of r2 over r1. And this is going to be the flux. And simply to get the self-inductance, we would divide it by the current. And so we get this, which is also equivalent to what they give in a textbook.